athletes, whoop whoop. All right, let's get into this. This is it's 8.1, which is functions and continuity. And for this entire module, we'll be talking about relations and functions. And it is our learning target today is I will determine the continuity of functions. So first things first, let's go ahead, do our warm up, read it. I'm gonna take my traditional sip of coffee. Pause this as you need it. Anytime you want to try out a problem, I'm assuming you're working ahead when I give you chances to do it, and then we'll talk about it. Ready, set, go. Awesome. I'm assuming you read about Anita making chicken noodle soup. The recipe calls for 3 times as much broth as meat. So if it's 3 times as much broth as meat, then our meat is going to be X, right? And our broth is going to be Y. And we know that for every whatever of meat, we need 3 times that of broth, right? So if I have 1 meat, I'm going to have 3 broth. If I have 2 meat, I'm going to have 6 broth. See how that works? Just multiplying times 3. And we're going to have that Y equals what? 3 times X. Okay, nothing big there. Awesome. All right. Take a minute. I know this isn't near as nice as the computer when it has the nice vocab, but I didn't like necessarily their definitions for some of these. So the domain is the set of X values. What are X values? They're the inputs. They're the independent variable, right? The range is the set of Y values, which is the output of a function or the dependent variable. Continuous function, a function that can be graphed with a line or unbroken curve. In other words, it's continuous if I can put my pencil on it and draw without picking it up. Discrete function is a function in which points on the graph are not connected. Okay, they're just dots. But it's still a function. In other words, I passed the vertical line test, but it's just dots. Okay, pause this, write all that down. Good stuff. I'm moving. Ready, set, go. Okay. Take a minute. Go ahead. Let me zoom out just a tad. And I want you to draw these graphs. Now, full disclosure, I drew a big one, not realizing I needed 2, so you can take a moment, draw them like I did. The big one's linear, going to be for a linear graph. The small one's going to be for a nonlinear graph. But just draw yourself some X, Y axes. Make sure and label them X and Y. Maybe better than me so the Y doesn't look like an X, but there you go. Okay, let's move on. We're going to go to the slides. Pause this if you need to, but draw, basically just draw 2 sets of axes in each box. We're going to talk about what it means to be a discrete, continuous, or neither discrete nor continuous function. And here we go, as Mario would say. Okay, sorry we blipped there for a second. So we're talking discrete. We've already had the definitions of that. Now, neither discrete nor continuous just means it doesn't fall into either category. It has elements of both. We'll talk about that in a minute. Let's talk about domain. The domain of a discrete function is the set of individual X values. That makes sense because it's just individual points, right? In fact, why don't you go ahead and make that little graph. Doesn't have to be exact, just get some dots in a straight line or graph. You'll notice that the domain of a continuous function is a single interval of all real numbers. So in other words, if we look at this right here, this is all real numbers from left to right. This is forever. I know it's going down too, but we're just looking at the domain. It's forever going left, it's forever going right. So it's all real numbers there. Go ahead and graph yourself that continuous linear function. I'll show you mine when we're all done. Now notice this one right here. It's kind of weird. This is a neither. It has some dots. We see a point here. Boom. Looks continuous going that way, and it looks continuous going back, but there's a break right here. And that looks kind of like a discrete function, right? Well, when you have elements of both continuous and discrete, it turns out it's a neither. That's just, I know, really fancy math name, right? It's a neither, okay? You're going to see the same thing if it's nonlinear. So just go ahead and draw, the nonlinear dots. Still a function, it's just discrete. The second one, again, still a function. It's just continuous, right? It's nonlinear. And the last one, we have a little bit of elements of both. We have the curve going down to the left. You see me looking down because I'm drawing the same thing you are. And a curve going up to the right. If I were to snap back over here, guys, here's what I'm looking at. I just went ahead and drew the dots, right? So it's not that hard, guys. If there's dots and only dots, it's discrete. If it's unbroken, it's continuous. If it has a little bit of continuity, but then a lot of discrete too, you know, some breaks in it, it's neither. Elements of both is neither, okay? Awesome. All right, we're going to go ahead and go to the next slide. Okay, here we are. Let me drag my picture up for a second. It says, determine whether the function is discrete, continuous, or neither discrete nor continuous. Well, clearly it's an unbroken curve. You'll see a picture of this, by the way, on the bottom of your notes. Any of these slides I go through are going to be in your notes. I'll let you know. We'll go back and forth so you can kind of see what I'm doing. If it doesn't have any breaks, it's what? It's continuous. Oh, that sound. Yeah. Okay, part B, drag the domain and range of the function to the appropriate. Well, domain is x. Well, notice this is forever going up and to the left, forever going up and to the right. So it's going to be all x, okay? So all real numbers in the domain. And the y, notice, it has a bottom right here. So it's everything above that going up forever, but it's right here. And this is at what, -3? So that would be y is greater than or equal to, -3. Hey, here's that uncomfortable sound, which I'm starting to love it. Okay? All right. Looking back, guys, you'll see down here, that's what I've done. Just circle continuous, put all real numbers x, y is greater than or equal to 3. And I always just put a little x and y, you know, at least for you guys to remind myself what domain and range are. Okay, have this written down, reset, we're moving on. Remember, you can always pause anything you need to. Okay, we're going to go back and forward a lot between graphs or the slides. So let's go to the next. Okay, so we're talking about a cafe. It says the cafe sells coffee beans by the pound, up to 2 pounds. For the large amounts, they sell prepackaged bags of various weights. Okay, so notice something about this. If we want to know whether it's continuous or discrete or what's going on here, and we're going to talk about the domain and range a little bit. You can see that on the top of the back side of your notes. Notice that right here, for up to 2 pounds, it's continuous because it's $8 a pound, which means I can buy parts of a pound. Now, once I get past 2 pounds, it starts adding a half pound in increments. So really up to 2 pounds, right? So up to $16 worth, because 2 times 8 is 16. It's going to be a continuous function, but then it starts stepping, right? Becoming discrete. So like right here, all of a sudden we step up to 2.5 pounds is $20, 3 pounds is $22. And it's not giving me the option of in between because it's not a per pound thing once I pass 2 pounds. 5 pounds is $35. So notice it's a little bit of both. So what is this going to be? We've already talked about that. It's going to be neither. And that's what these slides are really telling us right here. Let's get that out of the way. So, boom. Because the customers can purchase up to any amount of coffee, 2 pounds, the function is continuous between 0 and 2. So that's x is greater than or equal to 0, but less than or equal to 2. For larger quantities, what I was saying is discrete. The domain of the function, so again, x is between 0 and 2, and then, or x can be 2.5, 3, or 5, right? So that is the entire domain. Go ahead and write that down in your domain section. So we know it's neither discrete nor continuous, and we see the domain right here of x being in between 0 and 2 pounds, or x is 2.5, 3, and 5. And now let's talk about the range. The range is right here. Now notice, you would think, wouldn't y be between 0 and 8? No, because 2 times 8 is what? $16. So you're going to spend a range of y is going to be between 0 and $16. But then what else can y be? Or y can be $20, could be $22, or it could be $35. All right? So if you're looking back at the paper, sorry, I wasn't exactly positioned right. It should look right like this, where it's neither discrete nor continuous. Here's our domain. Here's our range. Again, pause this as needed. Okay? I'm heading back on up. Awesome. Let's get this ready for the next one. Isn't that just nice? Get a little Bob Ross conversation in there. Okay, I want you to look these are graphs of inequalities. And I'm going to show you three different ways to look at it: algebraic notation, set builder notation, which is essentially algebraic notation, and then interval notation. So we're going to talk about three different types of notations, and I want you to write these down as you go. So in algebraic notation, what we would say? We would say on this one, it's an open dot. Don't forget, guys, open dot means less than or greater than, right? But does not include that point. If it's a closed dot, so it's all colored in, imagine I colored that in real nicely, it's going to be the less than or equal to or the greater than or equal to. You may want to jot that down somewhere because I'm going to erase this in 3, 2, 1. Boom. So notice it's just x is less than 2 because it's shaded to the left. By the way, this is on your notes. Don't forget that. It's x is less than 2 labeled above. This one, we have a closed dot at -2 and it's shaded to the right, so that's x is greater than or equal to -2. This one's a little bit different. We have a closed dot at 0 and shaded to the left, so that would be x is less than or equal to 0. But we also have an open dot at 2 and shaded to the right, and that would be x is greater than 2. Now right here we have another situation where we have an open dot at -4, a closed dot at +4, and it's shaded in between. So we're going to draw x in between. We know it's x is less than or equal to that +4. But then, reading it from x's point of view, we know x needs to be greater than -4. Here, another way to say it is -4 is less than x, which is less than or equal to 4. And then this last one right here, everything's shaded in both directions, so that's all real numbers. Okay. Notice the difference between set builder. Set builder adds in, I'm going to kind of take a minute, write these down, please. This says this. We have this little squiggly bracket, boom, squiggly bracket, then we have x. This x right here stands for all x, all x. See this line right here? That stands for such that. Such that. I need to start writing cursive with this thing. So what does this say? All x such that x is less than 2. So notice it's identical to algebraic notation, except now we've added in this set and then, of course, the little squiggly line at the end. Okay? That's all it's saying. All x such that. Boom. All right? The big difference is down here. What's this saying? All x such that x is an element of the real numbers. That's what this stands for. Right here, that means element. And this R with kind of the double backside right there stands for real numbers. Real numbers. Don't get too thrown by that, okay? People tend to get thrown by this, but don't be. It's just a way of writing it, and then we close it. That's a way of saying all x, okay? Now, here's the one that's going to trip you out a little bit. I'm just telling you, it looks a little trippy, but it's actually the easiest way to write it if you can get used to it. So write these notes down. I'll show you what mine looked like in a minute. In fact, if you want to wait to see how I wrote it down, you're more than welcome to. I'm going to erase all this. Boom. Interval notation. Okay, here's interval notation. The brackets serve the same purpose as a closed dot. It means include this point. Okay? The curved end serve the same purpose as an open dot. It means don't include the end point. So this is include the end point, don't include the end point. And the left bracket is for the left side. Boy, I'm writing terribly. If we have a right bracket, it's for the right point. So the right side, the right point. What do I mean by that? Notice this. This is going forever left to negative infinity. So we're saying, hey, we're going from negative infinity. It has to be an open bracket like that because negative infinity goes on forever, so there's no point you can end on. It's infinity, right? The infinity stones. And then comma, and we have our 2 here because notice it stops at 2, but that point doesn't include 2, which is why we have that curved bracket, right? Just the parentheses, I guess, is a better way of saying it. These are the parentheses, these are the brackets. Okay. Now right here, notice we're going to include -2. So it's the bracket on the left side with -2 because it's saying include -2. But then we're going to go all the way to the right, so we're going to go up to positive infinity, which has that parentheses because you can't set an endpoint on infinity. Okay, right here just as 2 and 1. Right here we're saying, hey, we're going from negative infinity all the way to 0, but at 0 we're going to include that 0 point. And then over here, we're going to have a parenthesis because we're not including the point 2, even though we're starting there on the graph, and we're going all the way to positive infinity, which has to be a parenthesis as well because we can't put an endpoint on it. This one is everything in between. This is where it's easier. We start at negative 4, but don't include it. We end at positive 4, and we include it. That's why it's square bracket. And then the whole line is just negative infinity to positive infinity. That is interval notation. So let's take a look and see how I wrote it. Okay, I'm going to exit this out.